welcome to Wednesday night office hours. Tonight is 11. It is November. It's 11:25. It's November 25th, and tomorrow is Thanksgiving. So, I'm sure a lot of people are. Well, some of you may be traveling. Some of you may be quarantining at home. I don't know how many people are have questions, but as always, I am here to answer them. So as you have them, hit me up with them. Good evening. Good evening, Lauren. It's good to know I'm not alone. Yeah, I'm here and I'm available and I'm ready to talk about whatever you need help with. So as you have the questions, hit me up. Yeah, absolutely. Absolutely. Okay, Lauren, let me pull up the Lab 9 stuff. Let's see. Okay, let's see. All right, okay, yeah, so the EDTA. Okay, so let's. Yeah, okay. And actually. Mm-hmm. Kate, we totally can. We totally can. After Lauren's question, I will totally hit up that polyatomic ion. Okay, so let's talk about step 2. All right, and this might help clear things up. I don't know, but before we dive into like actually crunching the numbers, Lauren, let's take a minute to talk about what we are calculating in step 2. So actually, before we talk about step 2, so the overall goal, what we're after in this lab, is we want to know what the molarity of calcium ions are and the molarity of magnesium ions in a sample of hard water. Right, that's our goal. And what we're doing is we are using a titration with EDTA to determine the calcium concentration and the magnesium concentration. Now, from the EDTA titration, whoops, hang on. So from the EDTA titration, what the EDTA titration tells us, from the EDTA titration, we can determine the concentration i.e. the molarity of all metal cations in solution. All right, that's what EDTA buys us. In other words, from EDTA, we can get the molarity of calcium and magnesium together. All right, the ISE reading allows us to calculate just the molarity of calcium. All right, so the ISE reading gives us the concentration of just calcium. And if we subtract the molarity from the ISE reading from the molarity we get from EDTA, the concentration of all ions in solution, we subtract one from the other, we get the molarity of magnesium. So that's the overall strategy. We're using EDTA to find the concentration of calcium and magnesium, the ISE to just get calcium. We subtract calcium from calcium and magnesium, and now we have both of these locked and loaded. So that's how we get both of those things. Now, in step 2, so that's the general strategy. Step 2 is the EDTA calculation. In other words, step 2 allows us to calculate the molarity of calcium and magnesium together. So the concentration of all ions present in solution. Raj, you know the good stuff is just getting started. Okay, so let's take a look at the calculations for this step. To calculate the molarity of, to calculate the molarity of calcium together with magnesium, we need to know the total moles and the volume. So first, to get the moles of calcium and magnesium, all right, so both of them together. First, we take the volume of EDTA. So you take which is the volume of EDTA solution, which is measured in milliliters, and you have to convert from milliliters to liters. The reason why is we're also multiplying by the moles, the molarity of EDTA, which is moles of EDTA over liters. And then finally, we know it's a 1-to-1 mole ratio, that every 1 mole of EDTA that reacts with 1 mole of metal cation. So that's calcium together with magnesium. Oops. All right, so this is the setup for calculating the moles of calcium together with magnesium. Now this, just to highlight a few things. This right here is the volume of EDTA. This is, you take the final minus the initial. All right, because for your data set, they give you the final volume of the burette and the initial volume. You take that difference, that's the number you plug in here. We have to use the unit conversion to get rid of milliliters so that our volume in liters can cancel. Yes, so Lauren, this step gives you the total moles of all ions present. So the moles of calcium together with magnesium. That's what this step will give you. To get the molarity, you take the moles of calcium and magnesium, which you just calculated, and you divide it by, the volume of hard water in liters. And this will give you the molarity of calcium together with magnesium, which is, if you recall our previous slide, that is this first step. Getting the molarity, or I should add rather box this first step. Calcium and magnesium together. Does that kind of at least put you on the right track, or do you need me to dig in a little deeper to the calculations? I'm totally fine as well if you need more help. I'm here. I don't think it's going to be a crazy office hours. We'll have plenty of time to get through it all. Yes, with one caveat. So the ISE reading, is going to give you a value like 185 milligrams of calcium per liter. So what you need to do is you need to do a unit conversion to convert milligrams of calcium to moles of calcium. All right, so the number that you get for the IC reading is a concentration unit, but it's not in molarity yet. So before you can do the subtraction, you have to first convert from milligrams to grams. Right, so that milligrams cancel milligrams. And then you need to use the atomic mass of calcium, which is 40.08 grams of calcium in 1 mole. And then grams cancel with grams. And now your only unit left standing is moles per liter. And so this is equal to the molarity of calcium from the IC reading. Excuse me. Yes, Lauren, that is. I think you just put your finger on really the biggest challenge with teaching chemistry at distance is you're reading these labs, but you don't actually have. We haven't actually stepped into it and physically done the experiment, so it's just very, very, very abstract. It's kind of like trying to teach someone how to play piano without a keyboard. You know, it's like we're saying like, oh, well, imagine if there was a keyboard and you put your fingers on the keyboard and they made sounds. That's like what trying to teach a lab without being able to physically do a lab is like. And so hopefully we will, that the COVID vaccine will come out and we'll be back to normal instruction. Hopefully before too long. Hopefully we maybe, I don't know. I was about to say, hopefully we don't have to do another year of this, or maybe one more year of this. I have no idea. That's what 2020 taught me, is I have absolutely no idea what the future holds. But what you're wrestling with is truly the biggest challenge with online learning with chemistry, and that's again why office hours are here, so we can talk about the same calculations multiple times, because it takes that reinforcement to kind of get it through. So don't feel like bad or you're not a burden at all. This is here to support you, because in this kind of online education scenario, students need more support than usual, and so that's why this is here. Okay, Kate, sorry. I just saw your second question. First. Yes, yeah, it totally does. Like, and Lauren, you could imagine if this class were just a lecture, it would be fine. Like, it'd be fine if it was just a chemistry lecture, but labs, it's just a nightmare. Total nightmare. So, Kate, yes, one single electron on a central atom does count as its own unique electron domain. So let's take a look. You wanted to see ICl4 with a negative charge. Whoa! Faraj, congratulations. Where are you transferring to? So first thing we got to do is we got to set up the total number of electrons going down. Iodine has 7 valence. Chlorine has 7, but we have 4 of them. So it's 28. And then we have a negative charge, so that's 1 additional electron. Heck yeah. Our let's see, so 28 plus 8 is 36. And that is our electron budget. Now we're going to select iodine as our central. And we're going to attach all of our chlorines. 2, 4, 6, 8. That leaves us with 28 electrons. Now each chlorine needs 6 more, right, to fill out their octets. And we have, what, 4 of them, so 6 times 4 is 24. And so you can see that we are going to have 4 electrons left over. But first let's complete our dots. All right. Now, we have 4 more electrons to place. We're going to put those... Iodine can break the octet rule. So we're going to give those electrons to iodine. All right. Now, Kate, getting to your question, which was why does iodine have 2 lone pairs, even though chlorine is more electronegative? And the answer to that question the answer is all about minimizing formal charge. So if you calculate, so let's calculate some formal charges here. I'm going to clear some space. All right. So if we calculate the formal charge for chlorine, chlorine, when it's neutral, has 7 electrons. In this structure, you count 1 electron per bond plus all of your electrons in lone pairs. So chlorine has 6 electrons plus 1 bond. 7 minus 7 is 0. And you'll notice that all of the chlorines in this molecule have a formal charge of 0 if you do it for all of them. Now let's go ahead and do iodine. Iodine, when it's neutral, has 7. In this structure, it has 4 electrons, so that's 4 plus 1 per bond, so that's 8. 7 minus 8 is -1. So the formal charge for iodine is -1. Now, watch what happens to the formal charge, because remember, the best resonance structure is going to have minimal formal charge. Watch what happens to our formal charges when I'm just going to change the location of one of the lone pairs on iodine. So I'm redrawing everything the same except for one thing, and you'll see, because I'll change color. All right. Let's say we had decided to give one lone pair to iodine, but then but instead of giving both to iodine, we give another lone pair to another chlorine because, Kate, as you mentioned, chlorine is a third period element. It's allowed to break the octet rule. Why not give chlorine these lone pairs? Why do they have to go to iodine? Let's look at our formal charges. Now, this chlorine, 7 electrons when it's neutral. In the structure, it has 6 electrons plus 1 for the bond. 7 minus 7 is 0. All right, and same for this one. Same for this one. All right, let's look at iodine now. All right, iodine, whoops. Let me at least change up the color. Iodine has 7 electrons when it's neutral. In the structure, it has 2 electrons plus 1 per bond, 4 bonds. So 7 minus 6 is a positive 1. So this iodine has a charge of positive 1. And now let's take a look at chlorine. This chlorine, 7 electrons when it's neutral. In this structure, it has 8 electrons plus 1 for its bond. So 7 minus 9 is negative 2. All right. So when you compare these structures, I'm just going to clean things up a little bit. So let's compare these two structures. And again, we didn't even move the second lone pair away from iodide. We just moved the location of one lone pair. And we exploded from one formal negative to, in the first structure, right, we have one formal negative. When you look at second structure, you have 2 formal negatives and you have 1 formal positive. All right, so so that is the reason why both lone pairs go to iodine. It's the chlorines totally can house those electrons, right? The third period, but the best resonance structure will have minimal formal charges, and the only way you walk out with 1 formal negative with this structure is if you give them both to iodine. If you give the lone pair, so if you gave it 0 lone pairs, iodine would have a formal charge of positive 3, and then you'd have 2 chlorines with formal charges of negative 2. So the brief answer at the end is giving both lone pairs to iodine is the only way to minimize formal charges in this molecule. Dude, yeah. After taking 401, this is like, you're like, oh man, I miss the days where we could just draw dots, and we didn't have to worry about chemical equilibria or the Nernst equation. Um, yeah, dude, that totally makes sense. I mean, I don't know if Davis is going to be doing on-site education, if they're going to be resuming it in the fall or not. But if it's all going to be online, you might as well like save some money and stay home. If they start resuming, on-site education, then it might make sense to move in. But yeah, totally. I actually so I used to tutor at Davis, not for UC Davis, but I did some private tutoring for UC Davis OChem students. I used to drive out there and like park it in the library all day and just like meet student after student after student, kind of a deal. And I love the town and the campus. It's super cool. I spent actually, Raj, if you look at my YouTube channel, the banner photo for my page is actually the Shields Library. If you look at it, I took a picture of the Shields Library, graded out, and then did like a lightning bolt striking the center on the center panel. I don't know if you're familiar with campus now, but Shields Library is the main library on UC Davis, and that's where my panel. Yeah, totally. So I hope COVID calms down soon enough, with enough time for you to actually get to enjoy being there, taking classes there. I love it there. I would live in Davis if I could. I just think it's a cool town. It's, a college town, but it's still small. I don't know. The houses are adorable. Okay, Lauren, let me let me take a look. Okay. So looking at number 3. Okay, let's see. I feel like I'm missing something already. Oh, nope. Oops. Lauren, you got it. You just add the two numbers and divide by 2. It's exactly what it sounds like. Yeah, I used to private tutor students who were in a ton of different classes, like the OChem sections. Um, none of the honors kids hit me up, but the main OChem peeps totally would. Um, and it'll be on the quarter system. You won't even be on semesters anymore. It'll be 3 10-week quarters instead of 2 16-week semesters. It's going to be awesome. Probably a good idea too not to take organic your first quarter there. Um, yeah, totally. I think that's wise because it's going to move a lot faster than semesters. It's going to be 5 weeks you take a midterm, 5 more weeks you're taking finals, and that's it. There are classes that you'll take that will literally have 2 exams, one midterm, one final, and that's 100% of your grade. It's a different beast, but I know you'll be up to the challenge. Um, and you're gonna rock it. You're gonna love it. It's gonna be so rad. Dude, straight up. That's the way to do it. I went to a community college first, before transferring to UCI, and I had my first semester there. I took I took a gen ed class. I took physics because I didn't get my physics done before transferring, and so I was taking a physics lecture, physics lab, that gen ed class. It was like a sociology class, which wasn't bad. But then I also took, I'm spacing. I feel like I took 4 classes, but maybe I didn't. But I did take upper division organic chemistry. Dude, you can get it. You just got to study like nothing else. Like your life depends on it. And I know you can and do. And you do that, you'll be okay. Go to office hours, ask questions. One of the biggest changes from moving to a UC from a community college is you'll find a lot of the students around you don't hit up office hours very readily. And you just got to be one of those people who, like, you just got to not care about what people think or what other people are doing. Go to office hours, ask questions. It's worth, like I found, for me as a student, it was worth risking looking dumb to the people around me to clear up a misunderstanding that I had, because I was like, I don't care what these people think. All I care about is, do I understand what's going on? And if I don't, I need to fix it. So ask the questions, go to office hours. Most students don't, which is weird. Professors have office hours. Like every single class you take, professors have office hours where you just walk in and get help, and most students don't. It's crazy to me, but there's kind of like I think it's a little more impersonal because you're like in a room with 400 other people taking OChem, so it's a little intimidating asking questions or going to office hours. But if you approach it like you do any community college class, you'll be able to get the help you need, and you'll actually stand out to your instructors because they'll be like, whoa, this person's like trying, you know? Heck yeah. dude, you got to. You are paying for those office hours. You're paying for that access. It's not this free thing, you know? I would expect nothing less. Expect nothing less of you. Also, side note, that's how you get letters of recommendation when you're at a UC. Show up to office hours, like, work hard. They'll learn your names eventually, and if you're getting a good grade in their class, they'll hook you up. Yeah, totally. It's if you work hard for them, they will work hard for you. If you act like you don't care, they'll act like they don't care either. So it's that's what I found after transferring, that professors at a UC, because it's bigger, they got more stuff going on. They will totally meet you wherever you're at. If you don't care, they'll be like, sweet, I don't care either. If you do, though, they will totally care, talk to you, help you out. They'll match the energy you go in with. So that's the mentality I would keep rolling with. I don't even remember your grade, to be honest. Um. Oh. That is the truth. Dude, I miss having you in class. I wish I could teach every online class. I wish it could have been like our class, where we started with in-person instruction, so we actually got to like all know each other, and you know. Shoot, sometimes you're still the gunner. Sometimes you still are. So I think I'm gonna do an experiment. This next semester, I'm actually gonna be teaching a class. I'm gonna be teaching 2 classes at 2 different colleges out of my YouTube channel. Still teaching Chem 400 for Folsom Lake, but I'm also gonna be teaching a class at a community college, a different one, that's 100% online, and I'm gonna be doing an experiment. So I was actually thinking of you, Raj, because I'm getting ready to teach this class in January at this different community college, and it's going to be an intro class. And I'm actually going to be trying something different. I am going to be using YouTube still to like stream lectures and stuff like that for this class, but I'm taking a stab at using Discord to teach this new class. I'm gonna build a Discord server and just kind of see how it goes. Because they have a more kind of interactive online lab situation, and so I'm gonna try to use Discord for that end. And if I end up liking teaching with Discord, I'm still going to be streaming all my stuff through YouTube, but managing a Discord server to kind of add some extra interactions, add some study rooms, that sort of thing. And if I like it, then I might import it into teaching for FLC. But yeah, I know you, because I feel like you were the first person to make a Discord server as a study group for one of my classes, and so this is going to be obviously not just a study group because I'm going to be the admin, but as I've been like kind of looking into it, researching it, it made me think of my OG gunner. Dude, that's awesome. Oh. Dude, your class was really one in a million. Oh. Dude. I would OChem is my absolute favorite thing to teach. Um No, that's so sad. Winnie rocks. Um I love teaching organic chemistry. It's like honestly, I mean, you know me. You've taken Gen Chem from me. Like I get into it, right? There's some parts that I like nerd out about. Like OChem is a nonstop, like just love affair. It's just a torrent of stuff that is the the coolest thing after the coolest thing for me. Um, it would be like I I feel like it would be OChem for me is like teaching a class like the history of Star Wars or the history of Lord of the Rings or um, the history of like punk rock or whatever, like just something that I'm just so into, and then I actually like when I teach it I get to talk about it every day to humans who are showing up to interact with me. Heck yes. Heck yeah, it does. um it's on another level for me. And you know, I'm adjunct faculty, I'm part-time. And so you when you're part-time, you don't have say over necessarily what classes you get to teach, and the full-time faculty like teaching the fun stuff. And for me and for many of us, it doesn't get more fun than OChem. So, you know, maybe one day I'll make it full-time faculty, if not here, maybe somewhere, and I'll be able to actually teach OChem again. Until then, I am, you know, I'm teaching Chem 400, and I enjoy teaching Chem 400 at Folsom Lake College. Zero complaints, but the dream is to one day move back to organic chemistry, if I can land one of those sweet full-time jobs. Honestly, yeah. Honestly, it was one of the things that I loved when I was tutoring UC Davis students in OChem, is even though I was still teaching Gen Chem, it gave me like a taste where I actually got to talk some OChem with some people. And I miss it. um, yeah, because it's one of the things I miss about doing private tutoring is, even though I was teaching Gen Chem, it gave me a chance to kind of get into some organic stuff. I used to do all that before. Whoa, really? Foster's retiring? I had no idea that he was retiring. Oh man, maybe he's maybe he is um maybe he's planning. Dude, yeah. Well, I mean, like honestly, the distance education thing has been hard for all of us. Um, I think it's been particularly hard for the faculty who've been around longer. Um, just because I mean, like I'm a millennial. Like I I can still remember before the internet existed. But I like grew up with it and kind of came of age with the internet. And so it's like, even though it's been a challenge, I'm the faculty who are a little bit younger have, I think, had an easier time just because the platforms and stuff are just a little more intuitive. It's been rough. I was talking to a friend who who's a stenographer, and he was saying how a lot of the old guard faculty in the stenography program he graduated from have gone into retirement. Some of them electing for early retirement just because the distance stuff is too much of a challenge. So I think it's maybe for people who are already kind of close or near retirement age, it's just like, okay, this is where I make my exit. You know. Yes! Dude, you taught me the dab emoji. right, Lauren, let me pull up my textbook. All right, let's see. Chapter 9. All right, so let's start with 60. Oh. Well, this is 60 parts A. All right, okay, write the Lewis structure for each molecule or ion, and it is, so the molecule is H3COH. All right, this one, okay, this is going to have a fun twist to it. So first we're going to total our electrons. We have carbon, which has 4. Oxygen is bringing 6 valence electrons. And then hydrogen brings 1, but we have 4 of them. So that's 4, giving us a total of 14 electrons to spend. All right, now given a choice of central atom, given the choice between hydrogen and oxygen, oxygen is a better central because of the 2 unpaired electrons. It likes to make 2 bonds. But carbon has 4 unpaired electrons. So we're going to roll with carbon. Now, there's a trap here. The next step is attach all your other atoms to your central atom. If you do this, if you try to do this with this molecule, we have 10 electrons. We have enough to go 2, 4, 6, 8, 10, right? Subtract 10. But there's a problem. This breaks the octet rule. This is breaking the octet rule. Carbon can never make more than 4 bonds. So with this molecule, we can't actually attach everything to our central atom. We have to take a more measured approach. So we're still starting with carbon in the center. But we can only attach 4 atoms to our central. All right, and this is going to spend 2, 4, 6, 8. 14 minus 8 is 6. All right, but where does our other hydrogen go, right? We have to include, yep, Lauren, you got it. You can't break the octet rule. Whereas hydrogen, that fourth hydrogen still needs to be included in this molecule. We can't put it on our central atom. We also can't put hydrogen on another hydrogen because hydrogen only ever makes one bond. So we have to take that fourth hydrogen and attach it to our oxygen. All right, and we'll spend another 2 electrons to get that done. All right, now when you look at octet rules, hydrogen satisfied, right? It only ever wants 2. It wants to be like helium. Carbon has 8 electrons. Its octet rule is satisfied. Oxygen, oxygen right now as drawn has access to 4 electrons. It needs a total of 8, so we're going to spend our last 4 to give oxygen some lone pairs. And this is the Lewis structure for, this is methanol, H3COH. So that is 60 part A. Whoops. So the other one is 64 A and B. Okay. Oh, no worries. Okay, let's take a look at, what was it, 64. Starting with 64A. All right, so part A, we need to draw a Lewis structure for chlorate. All right, so starting with chlorine. Chlorine has 7 valence electrons. Oxygen has 6, but we're dealing with 3 oxygens, so it'll bring a total of 18. And then we have a negative charge, which adds 1 additional electron. So what, 18 plus 8 is 26. All right, now, given a choice, we would rather have chlorine as a central atom because it's a third period element. It can break the octet rule. Next step, let's attach all of our oxygens. This will cost 2, 4, 6 electrons. All right. Next, each oxygen needs a full octet, right? It has access to 2 electrons as drawn. It needs 8, so we need to give each one 6. We've got 3 oxygens that need 6 electrons. 3 times 6 is 18. We have enough to go the distance, and we'll actually have 2 electrons left over, so we can complete the octet of each oxygen. All right. Finally, chlorine needs a full octet. It needs 2 more electrons. We have 2 more to spend, so we can give chlorine a full octet as well with lone pairs. Now, let's go ahead and so we have filled all our octets, but now we need to look at formal charges to see, is there a better resonance structure we can draw for this molecule. Because again, we want our formal charges to be as low as possible. The only way to assess whether or not we can minimize formal charges is by first assigning them. So when you look at oxygen, hang on. So oxygen, when it's neutral, has six electrons. In this structure, it has 6 electrons in lone pairs plus 1 bond, so that's 7. 6 minus 7 is -1. And if you look at each of these oxygens, you'll see that it has each one has a formal charge of -1. Now when we look at chlorine, when chlorine is neutral, it has 7 electrons. In this structure, it has 2 electrons in lone pairs plus 1 per bond. So it's 5. 7 minus 5 is +2. So as drawn right now, we have a chlorine, with a charge of +2, and each oxygen has a formal charge of -1. Now, we said that anytime you have this scenario, a formal negative on an atom that's next to a third period or lower element with a formal positive charge, that we could minimize our formal charges. And here's how. I'm going to actually open up a new slide. So I'm just going to redraw the loose structure we had. Nothing changed. All right, so we can minimize formal charges if we take a lone pair from one of our negative oxygens and use it to form a multiple bond to that positive atom. And since chlorine can break the octet rule, that's what makes this legal. So let's see what happens to our formal charges now. Once I add in all of our lone pairs. All right, so now we have a double bond between that oxygen and chlorine. The 2 oxygens, the one on the very left and the one down below, nothing's changed, so their formal charges are the same. But let's take a look at chlorine's formal charge. Chlorine has 7 electrons when it's neutral. In this structure, it has 2 electrons in lone pairs, plus 4 bonds. So 2 plus 4 is 6. 7 minus 6 is -1. Then when you look at oxygen, when it's neutral, has 6. In this structure, it has 4 electrons in lone pairs, plus 2 bonds. 6 minus 6 is 0. So chlorine still has a formal charge of +1. All right, and you'll notice, so we've decreased our formal charges, right? We've gotten rid of one positive and one negative, but we still have the same scenario. We have a negative charge on oxygen, a positive charge on chlorine, so we can minimize formal charges once more. If we take this lone pair and make it a multiple bond, we can get another resonance structure with again a minimized formal charge. All right. So let's look at the formal charges in this new structure. First off, the oxygen down below, nothing's changed. So That is a formal negative. If we look at this carbon right here on the terminus, oops, yeah, I want to do that in a different layer. There we go. This oxygen, when it's neutral, has 6 electrons. In this structure, it has 4 electrons in lone pairs, plus 2 bonds. So 4 plus 2 is 6. 6 minus 6 is 0, no formal charge there. Now if we look at this chlorine, chlorine has 7 electrons when it's neutral. In this structure, chlorine has 2 electrons in lone pairs plus 5 bonds. So 2 plus 5 is 7. 7 minus 7 is 0. So as drawn, this resonance structure has the correct formal charges, and we're at a place where they can't be minimized anymore because we don't have any more positives and negatives that we can combine. So this is the best resonance structure for chlorate ClO3 because it has minimal formal charge. Awesome. Okay, let's hit up part B. All right, 64 part B. Okay, you'll notice this one is similar, but I'm actually glad we're doing this one next because I'm going to show you it's going to be a very similar method, but I'm going to show you that we can kind of accelerate this process. All right, so let's go ahead and first do the kind of nuts and bolts part. Whoops, don't want that in blue. Chlorine has 7 electrons. Oxygen has 6. Here we have 4 of them. And so 6 times 4 is 24. Then we have a negative charge, giving us a total of 32 electrons in our budget. Oh, let's see, trace. Let me... Yeah. Yeah. You can only calculate one average. Trace. You can only calculate one average value, but you can't calculate a standard deviation because I believe you need 3 or more values to calculate a standard deviation. So you just have to take those 2 values, add them together, divide by 2, and that's your average. Even if it's asking you for more than one average or more than one standard deviation, that's going to be a mistake in the instructions. You're just calculating one average for Lab 9. Alrighty, so we're going to throw chlorine in the center. We're going to attach all of our oxygens, 2, 4, 6, 8, leaving us with 32 minus 8 is 24 electrons left in our budget. Each oxygen needs 6 electrons at this point. And we have 4 of them, so 6 times 4 is 24. We have just enough to fill out each oxygen's octet. Oh! Oops. Hi, Kyle. Good to see you. Yeah, that's the one thing with YouTube is people's handles. You're totally cloaked. I have no idea who Tracegate is, but now I do. Kyle, it's good to see you up in here. All right, so let's go ahead and calculate our formal charges here. Oxygen, each oxygen actually, well, oxygen when it's neutral has 6. In this structure, it has 6 electrons as lone pairs plus 1 in the bond. So that's access to 7. 6 minus 7 is a -1. Each oxygen will share that formal charge. And then chlorine has 7 when it's neutral. And in this structure, it only has 4 bonds. 7 minus 4 is a +3. So we have a positive, +3 on chlorine, and then a -1 on each oxygen. Now I want to point something out. In the previous problem, we had initially we had this Lewis structure for chlorate, ClO3 with a -1 charge. All right, you'll see we got 3 negative charges and a +2. This is the first one we came up with, and our final answer, the resonance structure, the best resonance structure, you'll notice that the +2 soaked up 2 of our negative charges, leaving us with 2 double bonds and just 1 formal negative. All right. Now notice what so that was the previous problem. Look at what we have here. Now this is if you can notice this will save you time on exams when you're drawing Lewis structures. You'll notice that in this structure we have 4 negatives. And we have a +3 charge on our central. Now check this. The previous one, we had a +2. It soaked up 2 of the negatives, and we ended up with 2 double bonds on chlorine. The same thing is true. The exact same thing will happen. You could draw these Lewis structures, you draw these resonance structures out step by step, or if you can recognize that +3 is going to eat 3 of the negatives, you can just jump straight to your final answer, which is you're going to have 3 double bonds to your central chlorine. With the 1 that still bears the negative charge. And just to be clear, actually, hang on. It's these lone pairs. You take 1 lone pair off, turn that into the double bond. That is how you get those multiple bonds to chlorine. And then this would be our final answer. Ah. Lauren, that is spot on. If you have a chance that it can be minimized, but you can't break the octet rule, then you're good as it is. So a great example of this would be nitrate. So if you look at the Lewis structure for nitrate, you've got a negative, just like we did before, a negative on oxygen, a couple of them actually, and then you've got a positive on nitrogen. So it might look like, oh, maybe we can minimize, but you can't minimize. You can't minimize because nitrogen cannot break the octet rule. Totally. Oh, dude, that's awesome. That's awesome. All right. Well, I am actually going to have to call tonight's office hours a little early. My poor wife is sick, and she just texted me that she just threw up, and so I it's pretty dead here in office hours, so I'm gonna go ahead and close it down, and go take care of her. Thank you everyone for showing up. Who did? We had some good questions tonight, and I hope you all have a happy Thanksgiving.